A couple of questions that came up during the break. Let me just go back here. These last series of slides was called Why Standalone Fences Are Suboptimal. So the question that arose was, does this mean we shouldn't use them? The answer is yes, and here's why. So clearly I need to add a slide saying, and key takeaway is, advice is avoid standalone fences, because they're very heavyweight and they prevent more optimizations than they need to. So they cost more in synchronization and they cost more on optimization. Now, having said that, if you are on a system that does not have standard mutexes or mutexes at all, or does not have standard atomics, and you want to write lock-free code, then you may need to use that. But those are getting more and more of a historical kind of artifact, and hopefully we will be able to get away from this world. Another one, if we go back a few slides, the question was, I mentioned fences together with ordered APIs. These are really, this is sort of a bucket of things you should try to avoid and use mutexes and atomics instead. But the ordered APIs are actually better than the standalone fences. The reason is because notice when you do an interlocked exchange, you say flag 1, address of, flag 1 to 1. I'm setting it. The synchronization, the fence, is associated with the store. That's so much better than what we had and prevents some of the problems that we had with the other, with the standalone barrier. However, it still has a problem that it's a full barrier. So on x86, or on Windows and x86, you'll see interlocked exchange is basically your go-to, and that's a full barrier. You do get interlocked exchange acquire and interlocked exchange release, which is variously well supported by platform. And you can use those also, and then you'll get pretty much what you would get with an atomic, but it still has the disadvantage that you have to write it at every point of use. If you just say the variable's atomic, then you can just use it. And that's really a nice place to be. So the point of this section is, here are the reasons, just so you understand why fences cost more, because they inject more synchronization and because they disable more optimizations. So now let's talk about other things. And by the way, one other person asked, are we going to talk about lock-free code examples, how to use atomics? Unfortunately, not unless we're going to go into the afternoon, which we can't do, we don't have time to do. So all of what we're covering here is, with just a few examples, the basic tools, just to understand how does the memory model work? Why does it work? How does the compiler and the processor and cache get to reorder my code and munge it in all sorts of bizarre ways that I don't even want to know about, and still get the right answer as long as I don't write erase? Because this kind of audience wants to know from the top to the bottom, wants to know the real reasons why. So we're going to talk about the truth and the real reasons why, even though it's a very frightening, deep well of truth. Let's talk about other restrictions on compilers and hardware, because again, this falls into the category of not learning how to use atomics, but I'm explaining how they work. And now here's another section on what the compilers and hardware have to do to keep your program happy. Let's say you have two global variables that are characters, C and D. Each one is protected with a different mutex. So I'm going to use C mutex to protect variable C. So there's my lock guard on C mutex to protect the write to C, and thread 2 protects D with D mutex, and then writes D equals 1. The question is this a correctly synchronized program? Or is there a race? Depends if they're on the same cache line. Where in the standard does it use the term cache line? Nowhere. So let me ask the question again. Is this a well-synchronized program, or is it a race? Yes. Yeah, so if they're on the same cache line. So it sounds like we've tripped over and impaled ourselves on this sharp spear a couple of times, and people understand the problems here. Let's just be very clear. The answer is, this had better not be a race. Like, it just had better not be. And the C and C++ memory models guarantee that this is not a race. If, however, you have a broken compiler or processor, which is getting exceedingly rare, but let's say you did. So if you see a problem here, here's what might be happening. What if, because these are two characters and they're really close together, and the compiler or the processor just really loves operating on 32 bits at a time instead of 8. Why would you ever want to waste your time on 8 when you can do 32? or 64. Let's just read 4 characters worth of stuff. There's my scratch pad. Read them all. Set just the one I care about. Set the bits of D, say, on thread 2. And then just blit those 32 bits back. And I only changed 8 bits of them, right? This is unsafe. Why? Now, this is not obvious, because at first you think, but I'm innocent, right? It's like the kid with the cookie jar, hand in the cookie jar. But I only took 1 cookie. I only wrote to the bits of D. I wrote back the same bits that there were there before, but you have now injected a write to a variable that is not visible in the source code for thread 2. So what? You might introduce arrays. How and why? That's correct. Why? D could be in that look. So in thread 2, say, if we're doing this in thread 2, you're also writing to the bits of C. And why is that a problem? It's unprotected. Does thread 2 have the mutex to protect C? No. So we would also be injecting a write of C. It's kind of like injecting a C equals C semicolon right there, think of it that way, without holding the mutex that protects C. That's injecting erase. And you'll be glad to know that the C and C++ memory models say this is illegal. You may not invent a write to a variable that would not have been written to in a sequentially consistent execution. Here's another example. Let's say I had exactly the same situation, but I put them in the same struct, right? And again, I do the same thing. I protect each character with a different mutex. Is there a race? And again, no. We guarantee that this is OK. You are perfectly allowed to reason that variables are independent. And it's up to you how you want to synchronize each variable. If you have 2 shared variables, go ahead and synchronize this one using a mutex and this one using atomics or a different mutex. And it doesn't matter if they're both characters and they're both adjacent. What this means is that the system, what does it have to do? Even if it lays them out together in the same cache line, that's OK. As long as it generates instructions that do only single character reads and writes from C and D, that's OK. Or if you are on hardware that cannot do that, it must inject padding so that when you write to the bits of C, you never touch any of the bits of D and vice versa. This is required. And it's important because you can't have a sane world unless you know exactly what variables are being written to, you, the programmer. You have to know this. There's a hand here and then a couple here. Let's start on the left. You're right. If you are on a processor that can only do 32-bit reads and writes, it better be adding lots of padding. It better be storing individual characters in 32 bits. But think about the alternative. If it's the way that we said here, because basically, if it only has a 32-bit read and write, it's as if you wrote this source code, right? It's as if you took the 32 bits, massed it out. If it can be injecting the equivalent of a write to some other nearby memory, you can't possibly synchronize your program correctly because you can't see what the variables are that are being written. Never mind that it could be somebody else's variable who you don't even have source code for, so you don't even know what the mutex is, if any, to acquire. You have to know exactly which variables are being touched and that you are only writing to the variables that you yourself mentioned. Does that mean if you pack, you use the guarantee? Where in the standard does it mention packing? So when you're doing packing, you might lose the guarantee. It depends. You should check your compiler's documentation and be careful. Now, this only applies. You only really care if you are intending to protect 2 different variables with 2 different synchronization. They're both shared, and they're protected differently, like with 2 different mutexes. If they're protected with the same mutex, like the same structure, yeah, go pad. Now, I'm going to actually talk about padding in a second, so let me hold that question, because it's so funny that you happen to ask that, because the next question is, what if they're bit fields? Which is an explicit case of padding. Was that your question, too? Perfect timing. Excellent. OK, your 20 bucks is coming later. What about a global variable s of type struct int c:9, semicolon, int d:7, semicolon? By the way, first of all, is everybody familiar with that syntax? Yeah. don't worry, those of you who didn't raise your hands. I didn't know about this for my first half lifetime of using C and C++. It's like, why would you do that? Well, sometimes data layouts, you want to match external data layouts or whatever. What this means is I have something which is nominally an int, but I don't care what size of int is. It is exactly 9 bits. And followed by a variable which is nominally of type int, but it's not really the size and layout of an int. It's 7 bits. Now I try to protect these two with different mutexes. Is there a race condition? Yes. Why? The compiler can, in fact, probably had better pack those into the bits of the same word. But when the follow-on from that is, how do I implement thread 2 without overwriting any of the bits of C? I've noticed I picked the smaller one, right? It may not be possible to do single bit. In fact, I don't know of a processor that has single bit reads and writes. It may not be possible to, and it would be hideously expensive, to implement s.d equals 1 without also touching some of the bits of C, because at least one of the bits overflowed into my byte. Thank you very much. And the reason this is a race, well, that is the reason why, but the legalese reason in the standard is because that C11 and C++11 say adjacent bit fields are one object. So the rule is any object you can protect independently, and we guarantee that everywhere. By the way, adjacent bit fields are one object, and this is the reason why. It may not be possible to do sane code generation. Scott, your hand was up a minute ago. Compilers can invent writes all the time, but they must not invent a write to a variable that you would not have written to in a sequentially consistent execution, which we're going to drill into deeply in a second. Let me hold a couple of questions because the next few slides might answer them, and then I'll take any questions that come up because there are several related cases. There are many transformations that hardware and compilers want to do on your behalf. Register allocation, speculative execution, that would, if they're done naively, which is the way that they've been done for a long time before threading was popular, can do this kind of thing, can invent a write to a location that wouldn't be written to. In fact, you've seen some of them. So the system must never invite, here's the summary, a write to a variable that wouldn't be written to in an SD execution. Why? Because you couldn't possibly know what locks to take. You couldn't possibly synchronize your program correctly then, because you don't know what variables are being written to. So consider this pattern. Let's say you have a shared variable x that is protected by a mutex. And so what you're going to do is you're going to say, if a certain condition is true, lock the mutex associated with x. Then sometime later, if that condition is true, so assume it's a static condition, it's not going to change the answer. If it was true, then use x. And then later, if the condition is true, unlock x. And the question is this pattern safe? So first of all, why would you do this? Well, because maybe you don't actually access x on most executions. So you only want to take the lock if you're actually going to be doing something with x. Maybe there's an optional path in the function. You get a Boolean in from your caller that says do extra work, and only if you're going to do the extra work do you want to take the mutex that protects the extra shared state. So you might do something like this. Is it safe? What do you think? What would you like the answer to be? Yes. What do you think the answer is? Sometimes we can be too jaded. The answers are yes and yes. You would like it to be correct, because I'm telling you, you would like it to be correct. And it is, in fact, correct in the standard. Oh, but the answer to part 3 is no, not every compiler may actually do the right thing here, and I'll show you why. Yes, it's supported by the memory models in C and C++11, because I can reason about this code, and here's the thing, right? Sequentially consistent means I can reason about my code. I can reason about this code, and I know just from reading it, and this is the sequentially consistent part, just from reading the code, that on any path where I might touch the shared variable, I have also acquired the mutex, because I say if the same condition each time, and it's not going to change. Assume condition doesn't change. Now, what if we take that middle part? So we're going to talk about this middle part, if condition use x. What if we take that And the compiler decides to speculate, predict, whatever, to reorder the code to say, you know, maybe I've instrumented this with profile-guided optimization. Or maybe I'm just feeling lucky. And I know that or suspect that most of the time condition will be true. And I'm just going to write to x. Here, let me just go ahead and write to x anyway. I'm going to write x equals 42. Then I'm going to test the condition. And if it's not true, I'm going to write back the old value. Is that a legal single-threaded, forget concurrency. If we were only in a single-threaded world, is that a legal optimization? Yes, perfectly legal, because it doesn't change the meaning of that thread. In a multi-threaded world, is this a legal optimization? No. Why not? We're inventing a right to x when condition is false. In fact, we do two of them. Right? In the original code, if condition is false, we don't write to x at all. In the revised code, if condition is not true, we've already written once to x, and then we do it again to write back the old value. If you're going to punish them bad, right? Because now in an erase condition, sometimes they'll see one value, sometimes they'll see the other, and they won't know what's going on. This is how you confuse programmers. So this is a compiler bug. If you see this, report it to your compiler vendor as to what were you thinking. What they were thinking was single-threaded. But this is an invalid optimization. And this can break patterns like conditionally taking a lock, because now we're relying for this to be true that I only use x if condition is true. And we're changing this from a conditional right to an unconditional right that we do always, even when we don't hold the lock. That injects erase. Similarly, what if, again, here's that example of a function that takes a parameter of do optional work. And if do optional work will take a lock, and then in a for loop or something, and doing some work, if do optional work will increment x, and then if do optional work will unlock. Well, if we take that middle part and we change the loop to this, which is a very common optimization to enregister a loop variable, like you obviously don't want to increment that shared variable in memory all the time and just be reading it across the bus. No, you don't want to do that. No, we'll just read it once into a register, increment the register, and then write it back out, except this write is not conditional. It will happen on every execution, even if do optional work is false, which will inject a write that is not protected by a lock, by the mutex lock, that injects erase. And notice it's not just I'm writing to a variable that you didn't mention. No, I'm writing to a variable that in a sequentially consistent execution you would not have written to. And you are allowed to do things based on knowing what you would have written to. And if I do this kind of thing, I'm breaking that promise. One last one, and then I'll take the questions that are coming up. It's great when you see the conditional one like we just saw here, if something plus plus. Here's another one. There's no if here at all. It's just for int I equals 0, I is less than v.length plus plus I, and then we increment x in a loop. This is conditional on the vector being non-empty. If the vector is empty, we will never execute the loop body. Therefore, if v.length is greater than 0, we're not going to take the lock. Oops. If we then do this in registration, which is a very common optimization, and make the write unconditional, we're always going to write to x, and again, we have this problem. So what do we do? Here's the final slide of this section, of this series. Does this mean like register allocation and all these things that have been so important for many years are a bad thing? No, it's just making unchecked writes or unconditional writes, injecting those is bad. So what you could do, for example, in a compiler, is you could say, I could register the loop variable, and at the end say, if do optional work, so repeat the test, then write x out. Makes perfect sense. And this will continue to be safe, and I've still got the benefit of registering the loop variable. But I haven't created a write to x under circumstances where I would not have written to it if I was playing by the program's rules in source code order. Or you can do what caches do. You can have a dirty bit. You can say, by the way, I'll set dirty to true if I ever increment the register, and then I'll say, did I actually do it? If I did, then unload the variable. Another third common one that didn't fit is to say, register 1, R1 equals 0, plus plus R1, and then if R1 is greater than 0, x plus equals R1. That's another way you can do it. Which will also save you the right if you wrapped around all the way in R1 back to 0, but anyway. Now, there were questions about this. Starting over here, though any ones that weren't answered by the subsequent slides. Did you have a question before? Was that answered? Okay. Next to you. So the memory model has been specified for a long time, but we've been programming with pre-threads and it's been working. Well, it turns out that in general, we've been writing multi-threaded code using C++ for a long time. So mostly, we've just been codifying things that hardware and software vendors have already been getting right for us, just because we realized it's the right thing to do. Most compilers, even before the C++11 memory model, did not have these bugs. Some might have, and this is now going to expose that because more people are going to be relying on the standard guarantees. And instead of filing a bug report saying, I didn't like your choice here, they say, yeah, whatever, the international sign for unfiled bug, is that they can now say, no, you're not conforming to the standard. No, that really is a bug. Now you really have to fix it or you can't call yourself conforming. But most of these, just to write sane multi-threaded programs, have had to be already in place. But now they're being codified and made very explicit. Yes, the read of X is outside the condition, and it turns out that you can show that it has no side effect, because, for example, and it could be racy, because it could be outside the lock, but you can prove that it's, and I hate to say these words. Let me get myself together. This is very hard to say. It is a benign race. I feel dirty now. Because there really is no such thing as a benign race, we've learned. A lot of people thought there was a benign race, but there isn't. There is no such thing as a benign race in source code. Take that for granted, basically, and you'll be safe. This one, the compiler can prove that in such a case, if I do this and read the bits of X, then if do optional work is true, I never use them. Or I never look at them in a way that could do anything other than create wonderful abstract random art bit patterns in these 32 bits that I never do anything with. Then I can say it's OK. Because then basically the one thing that trumps the memory model, and basically the memory model supports, is the as-if rule. It trumps all optimization. Because if the compiler can prove, which is hard to do in a multi-threaded program, which is why we need synchronization. But if it can prove that a transformation has exactly the same effect, and you can't tell the difference, it can do it, no matter what else the standard may say. It's just in the multi-threaded world, there is much less it can prove, and so it really needs your help. In a single-threaded world, it can do all sorts of juicy stuff like this. Was there another question over here? Yes. Does this mean that single-threaded code is now pessimized? You have to take this care for any variable that may be shared. So if you're in a completely single-threaded environment, ignore all this stuff. You won't be using mutexes and atomics anyway, and your compiler, you can tell it in single-threaded mode. There's usually a mode where you can say, just go nuts. However, if you are compiling code that may be used in a multi-threaded program, and the compiler can't prove that a certain variable is unshared, then it has to be conservative like this. The good news is it doesn't actually hurt you too much, because think of what you're doing. You're taking your program, let's say take one thread in isolation, that we could just optimize every which way from Sunday before. And what we're doing is judiciously adding in certain places saying, and here don't move things down, and here don't move things up. But mostly we've tried to be very, very lightweight and not touch a lot of stuff. That's why we tried not to do more synchronization than we need. And many of the optimizations fire just great. You typically don't do atomic operations in a loop that's doing lots of other stuff, right? So usually loops get out of jail free card, which is where a lot of your optimization comes from. So keep synchronization operations out of tight loops, unless you're implementing a lock-free algorithm or something, or a lock yourself, a spin lock. And the performance overhead will be very small. It'll be just enough, and maybe a little bit pessimistic, but to avoid injecting races accidentally, because nobody likes that. Let me continue and with a few other examples, and also give you a summary of what to do. If you conditionally take a lock, but one of these things happens where you're on a system where somehow a write gets invented to something that you wouldn't have written to, you have a couple of options. One is just replace the function with two functions, like the one that took the do optional work flag. Replace it with a function that always does the optional work and always takes the lock, and another one that never takes the lock and never mentions the variable. Because you'll notice what the race bait, what the bait was for the optimizer. It saw a variable being updated in a loop. It wants to register that. If you write a version of the function that always takes the lock and uses the variable, you're good. If you take one that never acquires the lock and never mentions the variable, you won't be tempting your optimizer into bad behavior. Or just pessimistically write only the second function, only the one function that always takes the lock whether you use the shared variable or not. But if you don't want to take the lock all the time, use overloading instead. That's a workaround for this bug. It is a bug. The original function is supposed to work, but if you encounter this particular bug, and it's still somewhat common on various compilers, here's what you can do about that. Any last questions before we talk about code generation and specific platforms? Do I know which ones it's common on? I know that the information, that this rule, don't invent or write to something that wouldn't be written to, and all the ways it can surface, are still in the process of being assimilated by optimizer writers. And it's not so much that there are always known bugs, although I've come across a couple and fixed them in my product, is that I don't believe anybody has done a scrub of GCC or of VC that I know of through all the possible optimizations to prove they never do it. So I think we're getting to the point where people are know enough not to add such cases, but I don't know if they've gone back and scrubbed everything. That's why this particular case, or I'm trying to be smart about taking a lock on, because I can reason on code paths. I happen to touch it even though I mention it. This is the one big case that's still probably bait for an optimizer to violate the model. So if you try to take a conditional lock, so hence know about this pattern and how to work around it if it affects you. Yes. So the observation is, again, let's see, what's a good slide to do this with? Maybe here, is if I'm doing this work, I'm reading X, I'm inventing a read to X that's not optional. I could be seeing a torn value, like you say. It could be racing with something, right? But the compiler can show it's benign because what do I do? OK, so I read a torn value. I read an impossible value into R1 because it happened to be in a race. Do optional work turns out to be false. This has to be true. Otherwise, there'd be no problem. I'd have the mutex, right? So obviously, do optional work is false. So I read an impossible value into R1. I then don't use R1. And then I further don't use R1 to write back into X. So I've read an impossible value and thrown it away. So it's because of cases like that that you can show, basically, injecting reads is much less damaging. Injecting writes is what you must never do. But injecting reads that you could show just get tossed if it turns out that you didn't need them in the cases where it would have been a race, meh, it's OK. Having said that, I still feel dirty saying the words benign race because we've really learned that races just aren't benign. But there, that's enough angst and anxiety for you. Let's talk about code gen and performance because it's much more interesting. Remember that we said software memory models have converged on sequential consistency for data race-free programs. You agree not to write a race condition and do it, then so help us, we will pretend to execute the program you wrote, and you can't tell the difference. We've required this and made it the default in our mainstream languages and memory models. Another fact of life, I mentioned this earlier, stores are more expensive than loads. You have to tell other people when you do a store. Loads you can do in isolation. Just read it into your register, keep it in your cache, you're perfectly happy. A store you have to write to main memory, you have to invalidate cache lines, propagate it to everybody. Stores are more expensive than loads because they do more work. They also typically loads outnumber stores. So the fact that in most programs, you're going to do way more loads, reads from a location than you are going to store to it. Both of these are reasons to really optimize reads or loads. I'm going to use reads and loads interchangeably, stores and writes interchangeably. There's two different words. Hardware architects use one, programmers use another, but they mean the same thing. Stores are more expensive, and because the loads are much more plentiful, you want to optimize the loads. Therefore, when we have sequentially consistent atomics, the kinds we've been talking about, there's going to be overhead because you're synchronizing, right? We can tolerate even some fairly high, but moderate but high overheads on the store side. If you're going to do a store release, that can do a bit more heavy synchronization, and we're okay with that. We can tolerate that. It doesn't cause us to have a bad day. But loads must be fast. Now, they may not be as fast as an ordinary load, but the guideline we used during the design of the C++11 and C11 memory models, which also applied to Java, some of the same people worked on that. I didn't work on the Java ones, I just worked on the C and C++ ones, is that we can tolerate maybe up to 4, 5, 6 cycles of overhead on loads. That's okay, but it better not be much more than that. Stores, we'd like it not to be as bad as Pentium 4, please, but 200 is a little excessive, but we could live with that, but we'd like less. But we can tolerate more on the store side. So it doesn't have to be exactly as fast as an ordinary load, but it shouldn't have much overhead, an SC load. Let's look at what real hardware does. On x86 and x64, here's the recommended code generation for, I'm just going to show load, store, and compare exchange, strong, so CAS, compare and swap. On x86, an ordinary load is a single move instruction. A sequentially consistent atomic load is an ordinary move instruction. This means there is no code generation overhead for sequentially consistent atomic loads on x86. Bonus, right? Also, on a store, an ordinary store is a move, but an SC atomic store is an exchange operation. So the exchange operation, basically, it's a locked operation. The lock prefix is implicit. You could write lock exchange, and it's the same thing. So it does a lock of a memory bus and such. And the CAS is also a lock instruction, a compare exchange, because you're going to compare the value and exchange it as a single instruction, which is supported in that x86 instruction set. So let's go back to this move here. This is great, right? Meh? Oh, come on, we just said that the stores loads want to have low overhead. We did it. But what? Why did you say meh? What do you mean? There's no free lunch. You got to pay somebody. Okay, so there's a realist for you. Dyed-in-the-wool realist. Okay, it's because we're paying all the time on loads. Not much. But the reason is because every load, it's not so much that SC atomic loads are as cheap as ordinary loads. Think of it the other way. Ordinary loads are as good as, are as strong as SC atomic loads. That's the way to think about it. That's why they're the same. So yeah, we have low overhead on loads, woohoo, but the cost of that load means you have to be paying somebody somewhere, greater restrictions elsewhere. Here, for your viewing pleasure, is a cut and paste with a few edits to make it fit in the slide from the Intel x86, x64 memory model, which, by the way, considering x86 has been around since the 70s, they finally codified and wrote down in, I think, 2008. Thank you, Intel. Because everybody knew what it was, but Intel wasn't saying. It wasn't good. Oh, we don't want to guarantee that. We might change it in the next release. No, we don't. OK, fine, we'll write it down. Notice some of the rules. On x86 and x64, this is now at the hardware level. Actually, at the processor level, not necessarily the cache level, but processor and cache, actually processor and down. Reads are not reordered with any reads. This is even of ordinary memory variables. That's really strict. It means I can't even say read X, read Y, and do it the other way around if I happen to have already had Y in a register, say. So that's very strong. In fact, the strongest possible memory model is full sequential consistency, which is now a pipe dream that will never be there again. x86, we've always said during standardization, is an example of a very strong model for two main reasons. First, it implements sequentially consistent atomics very efficiently, but also it gives you all sorts of guarantees, including way more guarantees, it turns out, than you really need. That's strong. It's on the strong end of the scale. Compared to sequential consistency, of course, everything's weak, but sequential consistency doesn't exist. It's a pipe dream now. On the current spectrum, x86 is on the strong end of the scale. It doesn't even do read-read reordering. It doesn't do write-write reordering with a few exceptions. You'll notice the fine print here. We go down to 14-point font here for you. Writes are not reordered with older reads. So if you have load, load, store, so read, read, write, we're not going to reorder those on x86. It's starting to sound very close to a sequentially consistent machine, isn't it? Notice I'm not talking about some of the cache effects and other things, but this is what the memory model tells you. I make all of these red because these are really guarantees we don't actually need. But they're there, so OK, fine, we'll take them. Now we get to one we do need. Reads may be reordered with older writes to different locations. So this is actually gives us some optimization flexibility. If I have a store to Y and a load from X, I can reorder those because they're to different locations. And reads and writes are not reordered with locked instructions. So you might say that's a good idea, but notice that means that every locked instruction is a full fence, not just acquire or release. It's a full barrier. Then we have all sorts of things involving L fences and S fences, which basically are not important for our memory model. We're just not going to use those, just like we're not going to use these first three guarantees. We do care about M fences, which is a full memory fence, full memory barrier. And we also say M fence can't pass earlier reads or writes, and that reads and writes cannot pass earlier M fence. So this basically says M fence is a full fence, locked instructions are a full fence, and we can do some read reordering, but everything else we turn off. So what we have here is overkill. It is much stronger than is necessary to implement sequential consistency for data race tree programs, because that's where you really want acquire and release. It gives you lots of other guarantees, which are pleasant, but not really helpful, because now that we know that modern Java, C++, and C programs need these guarantees, it's a very short list, acquire, release, compare, exchange, and you give us all these other ones, that's great, but we're not going to use them. They don't matter to us at the C, C++, Java level. Now, notice that I mentioned here reads and writes are not reordered with locked instructions like exchange, also in 14-point font. Exchange was the one that we used to implement the atomic store. That means that we have, like I mentioned, a full barrier here on an atomic store on x86, which is sort of unfortunate because really we just wanted a sequentially consistent release operation and let things float upwards across it. It's not that big a deal because, again, like I said, letting things move into a critical section, while legal, unless you've got unless it enables a major optimization like folding two different loops together, which is a big optimization, just moving a single load or store up across that isn't that big a deal. But still, it's not what we wanted. We wanted a unidirectional fence here, and we get a full one instead. But the good news is x86 is very friendly and efficiently supports sequentially consistent atomics. Because notice that there is some overhead on the right side, but that's OK, because we said we can tolerate moderate overhead on stores, just not on loads. So now let's take a look at exchange. If you know x86 instruction set, you might also say, I can think of other instruction sequences that I could use to implement an atomic store. For example, what if I used an M fence, a full fence, like we did in one of the other examples in source code, followed by a regular move, which I know is going to be indivisible and atomic? Would it be a good idea for a compiler to choose that code generation strategy? The answer is no. For one thing, now we're talking standalone fences again, which have the same problems in the instruction set architecture as they do in source code. So standalone fences cause pessimizations. Ordering should really be associated with a specific load or store, not be a standalone thing, because then you have to make it more heavyweight, like you do here. It has to be a full fence. But the second one, which is a much more important reason, is you want to link code together. You want to write code, compile it with two different compilers, link it together, and have it not fall over. This is considered a desirable quality, even in C++. So everybody on the same platform has to agree, OK, guys, this is what we're going to do, and the code generation we're going to use on this platform, All in favor of saying we're all going to do exchange I, and everybody in the room put up their hand and said, that's what we're going to do. And everybody better do it. And if you come across a compiler that issues an mfence plus move instead, that will work on all the code that that compiler generates, but you link it with some other compiler and it will fail. Usually in intermittent and curious ways that you will have not much hope of debugging unless you go into disassembly and see what's going on. Now let's talk about another Intel product, the Itanium. Itanium 64, although Itanium's been getting, has been getting a bit less use, it's still there, and I mention it because it's a very interesting memory model. It's actually a very well designed from a memory model point of view, even though as a commercial endeavor, the chip didn't do so well. In fact, if you look at the memory model in Itanium, you will see two very important things that will just jump out at you now that you've had this much of this talk. You will see a load as an ordinary memory load, and you will see a load dot acquire instruction. It's like, all right, somebody gets it. Look, there's an instruction for that. On the store side, you'll also see, helpfully, a store release. Now, the only fly in the ointment here is, remember we said there's plain acquire release, which is just only acquire and release. Don't go the wrong way across an acquire and release. But the acquire releases themselves could go the wrong way if there's a store load. A release followed by an acquire could float past each other. What we really want is sequentially consistent acquire release, which is exactly the same, except it doesn't allow that one reordering. What they implemented was plain acquire release, which means that on the store, you also need to put in an mfence. You need to do store release followed by an mfence, unless you can prove that there is no load acquire coming up subsequently. Because if there is, they could float past each other without that fence, which would cause critical regions to overlap, which is bad. It would inject races, deadlocks, and all sorts of funny things. So the code generation for Itanium is store release followed by a full fence. And this is OK because we can tolerate the expense on stores, right? Loads have to be cheap, so they got enough of it right that it works out well for us. And again, for the compare exchange, notice compare exchange has a compare exchange dot release, and for the same reason it needs an mfence as well. So I already answered the next question, why after the store? Purely to prevent a store release followed by a load acquire from floating past each other. Now, you might say at this point, well, let's talk about alternative code gen. What if on IA64 I just emitted this SC atomic store as a full memory fence plus an ordinary store? Would that be sufficient? And the answer is no, for several reasons. Now, you might have heard me mention a few times, and I'm hitting on this because it's so important and easy to forget. Acquire, release are a package deal. If you do a load acquire and you get some value, do not assume that has any useful meaning unless it was set by a store release. Because you store release something and you load acquire the value, then you get causal transitivity and all the guarantees that the world is saying. So load acquire, store release are a package deal. It might happen as a happy accident that you might get away with having an ordinary store do the right thing with a load acquire, but you're not even going to be guaranteed that on the next version of the chip necessarily. So acquire, release are a package deal. Always remember that. They go together. Another major thing is this wouldn't prevent, MF plus ST would not prevent the store release load acquire reordering, because then if you had a store release followed by a load acquire, the code gen would be full fence, store, load acquire. Fence is in the wrong place. It doesn't prevent that reordering. If you wanted to prevent that, you would have to actually issue mfence plus store plus mfence, even if you got away with number one not being a problem. And finally, everybody on the same platform had better agree what the code generation is, so you shouldn't just be making up your code generation. You should do what your processor vendor tells you is the right thing, so that you can link code together, the different compilers compiled, and have it be sane. Now we get to power. The PowerPC architecture, which is popular, say, in the cell processor. It's used for the main processor on a cell, and it's used in Xbox, for example, and in older Macs from some years ago. An ordinary load is a load. A sequentially consistent atomic load is a sync followed by a load, followed by a compare, followed by a branch conditional, followed by an isync. A store is sync and store. So we saw that pattern before, memory fence plus store. And a cas is actually a little loop, which you'll probably only execute once, but the loop is mainly there for spurious failures. A question: if we circle the things that might be problems, by the way, how many of you have seen or are somewhat familiar with the power instruction set? I know a few of you asked me questions about it, so a few of you do know, maybe half a dozen. Sync is the same as HW sync. It's a heavyweight sync. Isync is sort of a lighter weight sync for only certain kinds of things. You can almost get away with putting an LW sync here on the store side. If you know that certain instructions aren't coming up soon after on this thread, you could probably generate an LW sync as an optimization here. To be conservative, if you're compiling code in isolation, it better be a full sync. But this is the real bad one. Why is it bad, and how bad is it? Why is it bad, and how bad is it? Looks like a lot of stuff for a loop. Yeah, well, for a load, yes. That's true. It's a lot of stuff for a load. But I don't even care about that it's a lot of instructions. I only care about one instruction, the red one. Why is this bad, and how bad is it? So why is it bad that there's a heavyweight sync on a load? Because we can't tolerate that. Loads must be cheap with zero or at least low overhead. We're talking like maybe 4, 5, 6 cycles, not maybe 100. We can't tolerate that. How bad is it? This instruction, that sync right there, is half of the reason why relaxed atomics even exist in the C++11 standard. Those 4 letters are half the reason. Because IBM lobbied, to their credit, pointing out the issues with power and one other major processor, and lobbied for a couple of years to say, hey, look, we need relaxed atomics because we can't do sequentially consistent atomics efficiently on our platform. And so we have, as an option in the standard, we have relaxed atomics that are not sequentially consistent. Now let's go to current ARM architectures. ARM is, you might have heard of that chip. It's kind of interesting and being widely used these days. In fact, you probably have, I would guess that the average number of devices that each of you are carrying right now with ARM processors is probably 3. You probably have a tablet, you probably have a phone, you probably have something else. So you're probably carrying lots of ARM processors on you right now. Don't worry, they've already taken over the world. There's no reason worrying about it now. Notice that on ARM, an ordinary load is an LDR instruction. A sequentially consistent atomic load is a load with a DMB instruction, data memory barrier instruction. A store requires 2 memory barriers. Remember I showed you that alternative code generation for IA64, and I mentioned you'd probably need a barrier, a fence, plus an ordinary store, plus another full barrier, and we said why? Look, there it is on ARM. This is where we have the data memory barrier store followed by another data memory barrier. And for compare and swap, we have a very similar loop here in this area for what we have also on power. See that? That's the other half of the reason why relaxed atomics exist in the standard. If it weren't for those 7 letters, the DMB on SC atomic load on ARM, and the SYNC on the atomic loads, SC atomic loads on power, I'm pretty confident we wouldn't be even talking about relaxed atomics in the standards. They're there only because sequentially consistent atomics have a performance penalty that can matter on those 2 architectures. So if you think about how this looks on one way that we might sort of graph this, and this is a very informal graph, is on a scale of, say, ultra-relaxed to ultra-strong, fully SC. Almost nothing is up there, but everybody's got full fences, so let's put full fences conceptually up near the top. The original alpha, especially the first generation or 2, was basically unprogrammable. because it was so loosey-goosey, nobody could write any correct code or figure out what the tea leaves meant. So this is sort of our borderline of just beyond the border of actually usable. It was first generation alpha. They got better after that. Alpha sort of migrated up to about here. x86, x64, this is a rough characterization. Stores are much stronger than they need to be. Loads are almost as strong too, and so you could say on the store side you need an extra fence. The loads are in pretty good shape. But they're very, very close to what you need for SCDRF. But when you get it wrong, sometimes you have to reach up for a full fence. IA64 is very close. The loads are exactly right, a load acquire. The stores are the plain acquire release, not the sequentially consistent acquire release. So we incur the fence on the store side. And that means when you hit one of those stores, you have to reach all the way up and grab a full fence in order to make the result SC. The key thing here is whenever you're south of this line, you have to do additional synchronization. And usually the synchronization doesn't just get you to the line, it makes you overshoot. And the weaker you go, generally the heavier thing you need to reach for. So that in theory, weak memory models give you more, in the hardware, give you more performance, in theory, but sometimes you have to synchronize. You need a coherent view of memory. When you do, you typically need to reach much further than would have otherwise been necessary. And it turns out that in many of the cases, you overshoot and end up being awash or even being pessimized because you need to reach for something much stronger. So Power and ARM both have much weaker memory models than x86. And for that reason, you have to reach for stronger fences. And because they don't have something that's exactly at SCDRF, you have to reach further higher and overshoot. For the same reason as you saw when you wrote explicit fences in your code, it disabled other optimizations. It gave you more than you really needed. But it was the only tool. You needed at least this much, and the only tool that gave it to you, at least that, was this one way up here. So you needed to overreach to get at least this much, even though you ended up with a lot more strictness and constraint than was desirable. So remember, we said that memory synchronization actively works against important hardware optimizations. We want to do as little of it as possible. We also said software memory models have converged on SCDRF, sequential consistency, the strongest thing there is, as long as, from the software side, as long as you didn't write a race. This means that every C program, every C++ program, every Java program is written to this memory model on the software side now. The software industry has converged. 10 years ago, nobody knew what it would be. Everybody was all over the place. We have now decided. We have converged on SC for DRF. That means that's what you need to support efficiently in the hardware too, and the hardware hasn't quite caught up yet. If you give stronger guarantees, like x86 does, then you're leaving some performance on the table because you didn't actually need to give us that much. If you give weaker guarantees by default, then you have to end up reaching for these heavyweight synchronizations that cost you more and are very expensive because you overshoot what you really needed because you tried to stay weaker than this. If you could only aim for exactly this target, you might not need fences at all. And you might only need 2 or 3 instructions or so as your primary instructions. Load acquire, store release, something like compare exchange or exchange, a handful like that would do you for many of the common cases. I've mentioned x86, IA64, Power, and I mentioned ARM, but I mentioned ARM, and you'll notice on the slides, it said ARM v7, which is the current shipping version of ARM Silicon. ARM v8 was announced officially to the public in October of last year. There is no shipping silicon yet that's been formally announced. Obviously, people are working on it, and their ARM's partners are working on it, but nobody has formally announced, to my knowledge, products, so we're not here to announce their products for them. But we know they're coming. The new generation of ARM-based products, which are about to hit the market over the next small number of years, are required to support 2 new memory model instructions, which may look really familiar. They are sequentially consistent load acquire and store release. This is the first ever time in the history of mainstream processors where hardware is now implementing SCDRF as a primary required supported memory model. And it makes sense because that's where the software has gone. The software is what you are going to execute, so you want to optimize for giving all the guarantees it needs, but why give more? That's only leaving performance on the table. And if you give less, then you have to synchronize more to get back up to what the software requires. So there's this mismatch today in Power and ARM between what the hardware does and what the software requires. ARM is now fixing that and equalizing it and getting rid of that mismatch. So in October 2011, they announced these SC load acquire and SC store release as a compulsory part of their new 64-bit architecture, because they're also 64-bit now, as well as their 32-bit architecture, industry first. That's for CPUs. Now, ARM also ships GPUs. And this is the only thing I'll say about GPUs this entire conference, but I know many of you are interested in GPU programming. And their memory models are quite different, and they tend to be separate from the normal world, the normal CPU world. ARM GPUs currently have something even stronger. They have a fully sequentially consistent memory model. And you can get away with that because you actually can only run constrained programs that are already constrained by memory ordering, and so you have less worry about doing that. It can be made much more efficient. ARM has announced also, and allowed me to say, that their future GPU roadmap has the GPUs fully coherent with the CPUs. So unified shared virtual memory, that's where the entire GPU and CPU industries are going, is to shared virtual memory. And they will likely add an SC load acquire and SC store release to their future GPUs also, as part of unifying the memory model. And here we see the industry converging in software already and now in hardware on SC for data race free. Intel could also do something where x86, which is currently slightly too strong, they could get some of the performance back on the table, but they don't really need to, as near as I can tell. They know best what the performance is that accrues from having too strong guarantees. It doesn't seem to hurt them too much. They run things pretty efficiently. Their power issues are mostly in other places, as far as I know. But Intel might also come down from being as strong as they are to supporting this as well, whereas ARM is coming up from being weaker, which costs more because you overshoot and do heavier sinks. So it's interesting to see the industry converging here. By the way, not to leave IBM out, IBM has also said in private mail, and have allowed me to say here, that they intend to also give better support and more efficient support for sequentially consistent atomics also on the power architecture in future releases. They are not saying whether that will be this kind of SC acquire release instruction or not. They'll decide that, or maybe they'll just make the existing instructions and barriers more efficient. But either way, you will have less reason to use relaxed atomics, even on those architectures. So ARM v8 is the first one that nails the bullseye. And so we're looking forward to Silicon, because right now it exists on paper, and we can't buy products that run it yet. But it has been formally announced, and those products are coming. This is where the industry is going. Which brings us to relaxed atomics. Any questions about code generation and performance on Power ARM and ARM vNext and Power vNext? So where's Intel on that? Well, Intel's already in a pretty good place. They may. So this is a bad place to be down here, because you have to overshoot and use these heavyweight barriers and throw your weight around on the memory system and choke everybody and stop the world to get up to here, because you tried to play too loose and fast and loose. Intel, turns out, has more guarantees than you really need. And it could actually relax some of those. Now, whether their architecture is amenable to actually taking advantage of that is another question. And remember when I said you have, say, a store release, instead, right now they have a full fence for the store, which means you can't move instructions up across it into the critical region. So if they made that just a real release, you could float instructions up. A lot of the time, that won't do you that much good, because moving a single instruction or two up isn't going to do you a whole lot of good. And you don't generally want to move things into a critical region anyway, right? Because you're doing more work while holding the mutex or whatever, right? You actually don't want to do that usually. Imagine, however, you had for I equals 1 to a million, do something with a sub I inside the loop, a store release, followed by another for I equals 1 to a bazillion, do something with a sub I. Today, I can't merge those loops because of the full barrier. I would love to move that big, expensive loop up into the critical section, which you'd normally never do, so I can combine it with the one that's already touching a sub I, and I'm actually eliminating the loop. That's the kind of thing that I would love to be able to do that I can't currently do on x86 because of the full barrier. Now, the good news is your compiler can do this, because your compiler knows that it's really a release barrier. It's just then when it emits the code, does the code generation, on x86, it doesn't have a way to say acquire release, so it does pantomime and says exchange instead, right? It says, okay, this is heavier than what I need, but it's sufficient, but you'll still get that optimization in software. Given that you get that optimization a lot of the time in software, and that single instructions don't really matter so much, there's less of a performance carrot, but they'll do the workload tuning and decide whether it makes sense to follow the same route as these guys have done. I would be shocked if 20 years from now, going into the far distant future, we didn't see all mainstream processors have these instructions. But if you're close enough, then you don't have the incentive to do it. These guys have the real performance incentive to fix the problem, because they have a performance problem. Intel currently doesn't. Oh, sorry, let me take you, because I'm trying to spread it around a bit. I don't think you've asked a question yet. Let me put a hold on that question. The question is, yes, but this all assumes cache coherency. Yes, we have a half an hour. Let me see if we can get through these optional parts, because I have a slide that answers your question. Yeah, but it's right. And you remember at the very beginning of the talk, I said this assumes, for it to be merely this hard, we assume coherent caches. So let's get into that. Let's talk about relaxed atomics, because, and I really want to be very clear here, I am not recommending you use them. They're very dangerous. At the same time, I want to admit that on power systems and on ARM v7 systems today, in high performance code in loops and with very high core counts, like 1,000 plus cores especially, but also in loops on smaller ones, you do have a performance carrot where you may care to reach for this very, very sharp tool sometimes. So if you're doing high performance work on ARM-based devices like many modern tablets and phones, okay, let's talk about stuff that, this is the section I hoped I would never need to give a talk about. And here we are. During the memory model discussions in the 2000s, one thing that kept coming up over and over again was sequentially consistent is so strong, and it's a penalty on power and on ARM. Couldn't we get just a little bit more relaxed than full sequential consistency? Couldn't we weaken it just a little bit? Turns out it's like being a little bit pregnant, because once you've relaxed it a little bit, like IBM in particular invested a lot of time with world-class experts who came back with many proposals, and others as well, but IBM really did a lot of good work here, in proposal after proposal in these meetings of, well, what if it was fully sequentially consistent except only for this one rule, or fully sequential consistent except for only this one rule and this nudge in this case? And every single time, after anywhere from 20 minutes to 2 hours of discussion, we would come up with, okay, if we do that, okay, then this example still works, okay, but what about this other example? And what about this other example? And after 20 minutes or 2 hours, it would turn out that the answer, eventually you would get to an example where the answer was, from the people proposing this relaxation, of, I don't know what that means, or no, that is broken. So even the world-class experts who are proposing just a little bit weaker than sequential consistency, it turned out didn't fully understand their own proposals. This is not to say that a little bit weaker than SCDRF or a little bit weaker than SC might not exist, but if it does, we don't know what it is yet. We don't know what that set of rules is. We have not discovered it yet. So way up here is full sequential consistency. We'll weaken that as our blessed memory model in software to sequentially consistent as long as you didn't write a race, which allows us to do a lot of optimization. And the next step down that we've discovered, they all seem to be down here. We haven't discovered the next ledge yet. Relaxed atomics are all down here. So what we've essentially done is built our programs as a city on top of a cliff. We really want to stay behind the sequentially consistent wall, the fence at the top of the cliff. But if you really, really want to go swimming down in the murky depths, let's talk about relaxed atomics. And of course, while we're swimming down in these depths, you might think things are going well, but you might not notice that your transportation home is leaving. It is very easy, once you start reaching for non-sequentially consistent atomics, to not realize that your code no longer means what you think it means. It becomes extremely difficult to reason about. Let's talk about why. My advice on relaxed atomics is don't go there. However, it's not just me. Quoting Hans Bohm with his permission, I would emphasize we've taken great care in the C++11 memory model that without relaxed atomics, simultaneously really means what you thought it did. Think about this. This is a disturbing statement to make. As soon as you go with relaxed atomics, you are losing sequential consistency in its ordering, and you are starting to lose causality. You're starting to lose the idea of simultaneously. You remember we talked about that we had that guarantee where if thread 1 set x equals 1, thread 2 set y equals 1, that all other threads would see them in some order. One would run first, then the other. Now we're starting to get into the realm of where time warps in different ways for different people, and there is no more consistent view, where A can happen before B and B happen before A in the same program. And it becomes very hard to reason about correct code. Now, having said that, there are some legitimate use cases, like reference counting, where you can get by with something weaker, and some hardware imperatives on power and on ARM. So let's talk about them. Here are the things in the standard that let you reach for the very, very sharp tool. The default pretty much for everything is sequentially consistent. If you explicitly write this in a lot of places, it has no effect because it's the default. So go ahead and use this one all you want. But you're wasting time because it's white space. That's the default. If you want to reach for something weaker, the very weakest is relaxed. Relaxed is like very, dude, you know, okay, like this is going to be atomic, but it's not, it's going to float around like wherever. So that's what it's saying. It's going to be atomic, all or nothing, but there's going to be no ordering guarantees. So remember, all of these affect only ordering. Atomic variables are still all or nothing, indivisible reads and writes. But they can float around now much more. In between are some usual suspects. Look, memory order acquire, memory order release. Memory order acquire release, which is the only difference between this one and this one basically is that this one is not sequentially consistent. So it's a plain acquire release, roughly. There's this other thing over here called memory order consume, and it's sort of like acquire release, but it's about dependencies also, and it's a little looser and very weird. And you also need the carries dependency attribute, which attributes are evil anyway, and you need kill dependency. I'm not going to talk about this. Atomics are already very hard. These are almost impossible, except for world-class experts, and this is harder than that. I know the people who write I know, Paul, if you're watching this, and others, who actually know how to write memory order consume. Yes, but there are so few of you. So a word from the standard. Memory order relaxed, no operation reorders memory. This is the definition pasted out of the standard. If you have release, acquire release, or sequential consistent, a store performs a release if you give it any of those attributes, any of those orderings. Consume we won't talk about. And if you say acquire, acquire release, or sequential consistency, then a load operation doesn't acquire. That's from the standard, and it's basically what we would expect from the names of the memory order operations. Now, some combinations are nonsense. Like, for instance, let's say I'm doing a load. So I'm reading from memory, and the default memory order is sequentially consistent, of course, as all well-behaved things should be. In the standard, the requires paragraph in 29.6-13 says, you better only specify release or acquire release, or sorry, you better specify anything but release or acquire release. Why? Stores release something. Loads don't release anything. That makes no sense. A load can't release anything. It didn't do anything. It's getting something. It's acquiring something. So the standard actually says you shall not pass, say, a release to a load. It makes no sense. Loads are acquire, stores are release. So some combinations don't make sense, just remember that. There are a handful of patterns that are well known that can benefit from relaxed atomics judiciously. Even when you see them on the next slides, it's much better to wrap them in a type and then only use that type, and only the author of that type needs to know the arcane magic and convince himself that it's probably okay. Let me give you some examples. Let's say you have the following code. on the right-hand side, in the main thread, we launch a bunch of workers, then we go and we join with the workers, and then we read and output a count variable. All these other threads up here are incrementing the shared variable. So here they are. They're madly updating count over and over and over again. So I launch the workers, I'm updating the count, then I join with the workers and I print out the count. What exact ordering is needed on every atomic load and store, in this case of the variable count? What's the exact ordering we need? Acquire or release is usually a good place, a safe place to start, but relaxed where? So you're saying relaxed for incrementing the count. Now, by the way, this is a read, modify, write operation because it loads the increments and stores, but that's guaranteed to be atomic by the standard. But you would like to make that indivisible operation relaxed so it can float around with other memory operations near it. Okay, anyone else? What about this one? Would you make that relaxed too? You don't want it to float where? Above joined workers, right. Why? If it floated above joined workers, that might be bad. So let me point out something in the fact that I've said launch and join. Assume launch does something like new thread or std async, and join does something like .join. Those are synchronizing operations. Those are happens before inducing operations. So I am guaranteed that launch workers happens before I start running the threads. It makes sense. I mean, they can't start running before I launch them. And when I join with them, I know that all the work in all of the threads happened before all of the work after join, right? Which means basically I'm guaranteed that this code is running in isolation. Count is not a shared variable, so at least this one should be able to be relaxed, right? What about these ones? We're incrementing count, and if that's all we're doing with count, assuming I'm showing you all the uses of count, this is simply doing some sort of lazy count, potentially lazy counting, because you don't care if, as long as that plus plus count is eventually done, the only person who ever reads it is after the join, right? So you don't actually care if he moves around in this thread. You just care that he is eventually done, and we'll guarantee he's eventually done, we just won't say when, subject to other ordering guarantees. Certainly before the join, because that does induce ordering. Therefore, we can't use the plus plus operator anymore. We have to call the fetch add function because we're passing in an extra parameter. We can, in fact, put memory order relaxed and on both of those, on the fetch add and on the load. And this happens to work just fine for this kind of counter if you are doing nothing else with that count. Because you're just blindly incrementing it, and you just care that those increments finally all get done before the single read of it at the end of the program. In that kind of situation, you can show that there's this nice ordering, and you can get away with relaxed. Okay. Any questions about that? I just told you relaxed is really hard, don't do it, and then I showed you an example. Relaxed, yeah, sure, it works. Go ahead, go nuts. Remember all the if clauses, if this, if that, and you have to think about it. Now let's talk about a right way to do it. Instead of explicitly writing these memory order things, you should instead wrap it in a class. Have an event counter type and make count an instance of that type, and then just increment it and read it. Internally in its plus plus operator and in its implicit conversion to or its output operator or implicit conversion to, say, int, that's where you put in the memory order variables. But you make it atomic, and then you use the memory order operations explicitly, wrap it in there, then you only have to implement it once, and everybody can use it without having to think about, is this relaxed correct? Is that in every place they use the code? So use a type that encapsulates the desired semantics. And even then, write and read the documentation very carefully as to what ways of using this are safe. Because you can't, for instance, say, plus plus count, and then later in one of these threads read count, and necessarily make assumptions about ordering anymore. right? So you have to document. This is intended to be used only for blindly incrementing, and then after synchronization, reading from again, that kind of thing. The data member within it is atomic. So the event counter is just another class which encapsulates this. It becomes a thread-safe counter, basically, that is only correct, gives you the right answer when used in certain ways. But as long as you're using those ways, it's fine, and it encapsulates the atomic and the relaxed operations inside it where you don't have to see that ugliness. Is it worth doing? Hold on to that thought. Hold on to that thought, because I think I have a question about that on the next slide. Simple flag setting. So here's another similar example. Let's say I launch workers, then I set an atomic stop flag to true, then I join workers. Now, the workers are doing something in a loop, and eventually they check to see if stop is set. So by setting stop to true in my main thread, I stop the workers. And there could be more work between the launch workers and the stop equals true, but that's my signaling to the workers to stop what they're doing. The workers, on the other hand, as they're doing different work, they may discover dirtiness. And if any of them ever discovers dirtiness, they set a dirty bit, a dirty flag. At the end, after the join, I check to see if anybody set a dirty flag, and then I clean up dirty stuff. So now state exactly what ordering is needed on each atomic load and store for these two variables, dirty and stop. Let's start with dirty. Relaxed, relaxed, that looks a lot like our last example. Okay. What about stop? Acquire, that sounded like a question, or was that a statement? In between. Okay, yeah, I don't understand that, but I don't understand these either. So, acquire, release, anything else? Okay. Now that we've had a chance to think about it a little, remember we get that, the launch and join, I'm assuming that ordering. Thread exit happens before returning from a join. Dirty, like we said, can probably be acquire release. It's probably not, shouldn't probably be relaxed, but you may get away with relaxed here because now you're not just looking at the bit, you're doing something based on the value, which means you're going to look at other memory, which basically you normally would think of a release because I've now released it. Now, because you happen to know I've got a release acquire by joining the threads, that I've injected a release acquire in there, that may be good enough, and you can just go to relaxed for dirty. But it really is important and worth making your ears perk up when you see, hey, wait a minute, I'm saying if dirty, do something. That means I'm now going to do other stuff and maybe read other state, depending whether it was set. That usually implies a release. And the only reason I can get away with relaxed, actually, is because there's another release acquire pair in there somewhere that I can rely on being there. However, stop.load definitely can be relaxed because it doesn't publish data. It simply sends a signal. And you don't care when it arrived. You know that it will arrive. Because the main thread could have run faster or slower anyway. Each of the other threads could have run faster or slower. So if it's a bit delayed on the way, it's as if the other threads ran at different speeds. See what I mean? It's as if they ran at different speeds. So it's actually kind of the opposite of what we thought. It's stop that can be relaxed, and dirty that actually should be acquire release, although in this case we can probably get away with relaxed because we have another acquire release in the middle because of the join. Now the question, is it worth it? What do you think? So the good answer to every performance question is it depends. Is it worth it? And in particular, is it in a performance critical region of code where this overhead matters? In particular, look at what we're doing. We're in a loop. It might be a tight loop. If it's a tight loop, and if I would like to be able to do optimizations across loop iterations, then I would probably benefit from these being relaxed, at least the outer one. Because that means I might enable more partial loop unrolling or other kinds of optimizations that can be done across loop iterations. Generally, SC is fine, and you don't want to deviate from the true SC golden path But on power and ARM, in a very tight loop like this, you may well benefit. And even sometimes on x86, but especially on power and ARM, you may benefit in a very tight loop in this particular situation. What you'd really like to do is set a dirty flag type that could be set that wraps all this stuff for you. Now consider that in a different example, reference counting. We've got about 10 minutes, and so I'm going to go through as much as we can and then skip a little bit to the end because we're already into the as time allows materials, which is great, but there's a little bit I want to show you at the end. But let's look at this one more example because it's really current. Thread 1 is incrementing a counter, a reference count, such as when you copy a shared putter. Thread 2 is decrementing a reference count, such as when you destroy a shared putter. State exactly what ordering is needed. What ordering do you need on each of these? The answer is so not obvious. Increment can probably be relaxed. We believe that it is safe for increment to be relaxed. The reason is nobody is going to take an action based on the increment once you get past 1. Nobody's going to do something, and therefore you're not publishing any information that somebody's going to take a dependency on. Therefore, you don't have to worry about other things being also available, because nobody's going to look at something based on whether the reference count is incremented. When you go from 0 to 1, when the reference count is 0, by definition, it's not shared. So you don't have to worry about anything, because no other thread can possibly see it. This is a get-out-of-jail-free card when reference count is 0. When it's incremented to 1, it's still not shared, because the original thread that takes it from 0 to 1 is the only thread that can see the object. It's in the middle of constructing, say, the shared pointer and the control block. After that, once the shared pointer is wonderfully shared and lots of different shared pointers are looking at the same control block, incrementing it can still be relaxed, because all I care about is that if 5 people copy it at the same time, that I eventually get 5 increments. I don't care what order they come in. Nobody's going to take action based on whether I go to 3 to 4 or 4 to 5. As long as I do maintain the right count, nobody's going to take action on it. However, when I destroy, then I need to do an acquire release, because the decrement I'm going to now acquire, they're going to race with each other. So think about it this way. All the increments can be relaxed because they're just doing things nobody's going to take a side effect on. They're not going to do something because of. But you might get 2 threads that hit decrement at the same time. The last 2 shared pointers go away at the very same time, right? When that happens, they're going to execute this code in 2 different threads. One of the threads is going to set it from 2 to 1, and the other one's going to set it from 1 to 0. There better be a causal chain of events that all side effects that happened on the thread that changed it from 2 to 1 are visible to the thread that changed it from 1 to 0 before we delete that object. Otherwise, we might end up floating writes down to the widget after we've started trying to destroy it. So there has to be that causal dependency. Therefore, we need acquire release here. And it turns out you need acquire release because one of the threads, of the last 2 threads, one of them is going to be doing this, has to release it to the second thread, which does exactly the same line of code, which has to acquire it. So this had better be acquire release. There are other reasons, such as that you need the code to stay below and above, but this has to be acquire release. We are going to ship Visual C++ 2012 with a bug on ARM because we made that purely release, and that's wrong. And we caught it too late, about 2 weeks ago, as a result of preparing this talk, that we haven't had a chance to fix it. Now, you might say, wait a minute, you mean shared putter doesn't work? No, we would have made it a recall class bug. It actually opened it up before RTM went, the gold disk went out, because we did have time before that. But we did actually test on major ARM architectures and discover that the bug won't be exercised, and we can immediately fix it immediately after release and give you a small patch. So we didn't have to uncrate the release for this. But it would have, if it had been exercised, and it had actually manifested, which fortunately it didn't, this would have been a recall class bug. Fortunately, it's not. And we're going to fix it, and everything will be fine. And it affected only ARM, because x86 was already stronger. As a result of this, we did a scrub of all uses of memory order in our entire code base. There were 3 uses. One was incorrect, one was questionable, and so we just switched it to sequential consistency, and one was OK. And we're also instituting a rule that nobody may use relaxed atomics, even on ARM, without a thorough code review and getting an approved exception for using it. And I encourage you to do the same thing in your shops. I'm going to continue so that we can go on to why not release. If I did only release, then there's no acquire release, which means I'm not communicating, and release doesn't keep line B below where it should be. So the delete could start percolating up before I finish using the object. It turns out that on the major ARM hardware, this happens not to happen in this implementation of shared proto control block. So we get a free pass, but we still got to fix it. So we have a few other, we should encapsulate this with an atomic ref count if you really want to take advantage of this. I'm going to skip the double-check blocking and you have some other examples of how you can use relaxed atomics there. And let me go forward to Hans's quote, "The fences in the standard may be the most experts-only construct we have in the language," just to reinforce the point. Remember at the beginning of the talk, I stated a key assumption, that for it to be merely this hard, we're assuming the caches are coherent. It has been questioned, including somebody mentioned during the talk, is that really going to be true as core counts scale? I want to refer you to a key paper that was published last month in the July 2012 communications of the ACM. You might recognize these names if you're in processor land at all. Certainly Mark Hill is one of the gurus in the world on hardware processor design. So as soon as you see a paper with his name on it, it goes up like +3 credibility orders of magnitude. And here's a summary from the abstract. Today's multi-core chips commonly implement shared memory with cache coherence. Technology trends continue to enabling scaling the number of cores. The conventional wisdom says coherence doesn't scale with number of cores. And so some prognosticators, I love that word, got to use big words, predict the end of coherence. This paper refutes this conventional wisdom. And we predict that on-chip coherence and the programming convenience and compatibility it provides are here to stay. Right now today, it is true that I've spoken with IBM PowerPC architects, hardware architects, who've told me just last week, look, Herb, we still need relaxed atomics, especially for certain kinds of applications. Those are for 4,000 core count supercomputing applications. It remains to be seen whether relaxed atomics get relegated to only non-mainstream applications once ARMv8 and new versions of the Power architecture come out, or whether they'll disappear entirely, even for large core count machines. Either way, for mainstream programmers, my prediction is they are a stopgap that only exist in the standard because of temporary weaknesses in 2 popular architectures that are getting fixed as we speak. So relaxed atomics, really hard. Don't need them in the future, we hope. And if you do need to use them today, use these tools and wrap them in a type. A last word about volatile, because everybody asks about this. And we're about 2 minutes short, and I'm going to intentionally go about 2 minutes over into lunch. Java and .NET have volatile. It is not the same thing as volatile in C and C++. What they call volatile is what we call atomic in C and C++. Let's talk about what volatile really means in C and C++, because it's related to the memory model. Mutexes, atomics, memory barriers, acquire, release. This is your one bucket of things that goes together, and it's all about inter-thread communication inside the program, inside the memory model. These are your tools that we've just been talking about for half a day. They are synchronizing operations within the same program, within the memory model. What happens if you need to talk to code or hardware that does not obey the C and C++ memory models? then you reach for volatile. And for compiler-only fences, they are best thought of. A volatile variable in C and C++ is an unoptimizable variable for talking to something outside the memory model. And it is deliberately underspecified, so it has very few portable semantics should you choose to look. In fact, we really like the way it's specified. It's basically specified as an access to a volatile variable, a read or a write, is just like I/O. It's like reading or writing from disk. It is outside the memory model, which is a very clean definition. So here in one slide is the summary of how atomics and volatiles work together. Remember, the first is for inter-thread communication, the second for external memory locations outside the memory model. The first question is, are accesses atomic? Is each individual read and write all or nothing? For ordered atomics, the answer is yes, as we saw. For volatile, the answer is no, you don't get any such guarantee. You know, maybe on x86 if you align it just right, you happen to get it, but it's not in the language or library, it's not a guarantee. The next two lines are about optimizations. First, can I optimize? Can I reorder, invent, remove ordinary memory operations across these special operations? And the answer is yes in both cases, but a different set with different constraints. We just saw with atomics, I can do acquire-release ordering one way or the other across acquire or release. I can do a different set of optimizations on volatile variables. One reading of the standard is that it's like I/O. Another is that ordinary loads can move across a volatile load store in either direction, but ordinary stores can't. Again, both allow some optimization, but it's not at all the same kind of optimization. And finally, can I reorder these special operations themselves, volatile read, volatile write, say, or atomic read, atomic write? Can I reorder those among each other of the same kind? Yes, I can reorder atomics and combine them. For instance, if I have an atomic and I say atomic A equals 1, A equals 2, A equals 3, I can get rid of the first two and just say A equals 3. And it's as if that thread ran really fast and nobody ever saw the first two writes. I'm allowed to do that. I can always reduce the set of possible executions. Volatile says you have no idea what this is doing. You cannot assume you know anything. You cannot even do a simple constant propagation. You're not allowed to do anything to it. You cannot even assume that you write a variable, or write a value, and that you even can read it back again. So don't write a race condition or use non-default atomics, and your code will do what you think, unless you have compilers with bugs or you really want to know how to use current generation hardware, certain hardware, really well. So that's a summary of the talk. Now we're going to go to lunch.